හරි. අප පටන් ගමු. අද මම ඔයාලට කරන්න විශේෂයෙන්ම යන්නේ okay application of derivatives, not graph part. Application of derivatives, simple part. Today we can finish that. Application of derivatives. So we have real applications. I'm going to discuss that. Okay, right topic, applications of derivatives. Applications of derivatives. Here this is very simple part. Application of derivative, very simple part. Definitely question number 14 part B will be application of derivative part. Most probably 7 or 6 marks out of 100 you will get. 7 or 6. 6 or 7 mark out of 100 you will get for pure mathematics paper. Then here we mainly focus about real applications. Real applications. Then in day-to-day life, we think about maximums. Maximum and minimum. Maximum and minimum, especially we say local maximum, local minimum. Local maximum and local minimum. So two different things. So when you consider here this type of graph, we say it is maximum type graph, local maximum type, here local minimum. So here this point we say local minimum, here this point we say local maximum. Local maximum and local minimum. Okay. So when you sketch a tangent here, then it is surely parallel to x-axis. When you sketch a tangent here, that is surely parallel to x-axis, no? And also it goes like this way and it turn. Then this maximum point we call turning point as well, and minimum point also we say turning point. Both are turning points. So maximum point here at the maximum point when you sketch a tangent, that is surely parallel to x-axis. At the minimum point also surely parallel to x-axis. So when you consider here this point, if you sketch a tangent like this, and when you consider this point and if you sketch a tangent like this, so here positive gradient and here negative gradient. Obtuse angle, no? Negative gradient. Here acute angle, positive gradient. Here zero gradient. Here negative gradient. And here zero gradient. And here negative gradient. That's how gradient varies. Okay. So when you consider point somewhere here, you sketch a tangent and you sketch tangent here. Here positive gradient, here zero gradient, and here negative gradient. Therefore here gradient varies negative to positive, and here gradient varies positive to negative, and here negative to positive. Then that's how we identify a maximum and minimum. Here this shape we call concave down, here concave down, here concave up, here concave down, and here concave up type. Then here mainly focus about gradient, no? So in differentiation we know differentiation represent gradient. Therefore by differentiation we can analyze this maximum and minimum points. So here these two are, especially we say turning points, and again we have further turning points and inflection points, both we have. But in applications of derivatives we mainly focus about local maximum and local minimum. That's the thing. Really simple thing. Okay. Then here differentiation part very small. Then we have to do one differentiation of the function. Then further part Further part, just mathematics, okay? Okay, just write down applications of derivatives. Okay, write this way. Okay, write down. In day-to-day life, there are some variables. In day-to-day life, there are some variables which are varies with another variable or variables. Another variable or variables. Example, volume of a cylinder varies with radius and height. Example 2. Cost function of a sphere varies with the material. Okay, 2 examples enough. So now see, now you identify there are some variables or some quantities that varies with another quantity, no? So in such case, we have to maximize something or minimize something. So if we need to maximize volume, we have to do something. If we need to minimize cost, we have to do something. Then those things we analyze by using differentiation. Okay, write down. To maximize or minimize some quantity, differentiation is applicable. Okay. Now you sketch this one. Sketch the diagram. Here we call local minimum and here local maximum. Local mean only one point it happened. Local maximum, local minimum, gradient varies, positive to negative gradient varies. Here negative to positive gradient varies. Gradient varies positive to negative through 0. And here gradient varies negative to positive through 0. Here positive to negative through 0, here negative to positive through 0. Okay. Now further you consider, here you go from left to right. You go from left to right. So when you go from left to right along this curve, here increasing and then decreasing. Okay. Here decreasing, then increasing. Decreasing, then turn and increasing. Here increasing, then turn and decreasing. Okay. That's how we analyze. Increasing, decreasing. Here gradient positive, positive, negative, negative, positive. Okay, write down. Write down. The above local maximum or local minimum, the above local maximum or local minimum, the above local maximum or local minimum can be identified by differentiation. Because by the derivatives we can analyze gradient of the tangent, gradient of the tangent drawn to the curve at certain point, Therefore, by the gradient increase in functions, decrease in functions, increase in functions and decrease in functions can be analyzed. Increase in functions and decrease in functions can be analyzed. And also critical points within bracket turning points or point of inflections. Critical points within bracket turning point or point of inflections can be analyzed. Next line. By the second derivative, concavity can be analyzed. Okay. Now you sketch this one. See this. Here I told this before. Here local maximum, local minimum. Here increasing inflection, and here decreasing inflection. These 4 points we call critical points. And these two we say turning points. Altogether critical points. These two we say turning point. Sketch with me. Here point of inflections. So when you sketch a tangent here, that is parallel to x-axis. When you sketch a tangent here, that is parallel to x-axis. When you sketch a tangent, that is parallel to x-axis. When you sketch a tangent, that also parallel to x-axis. Therefore, all these cases gradients are 0. Critical point. Okay, we have 4 cases. And here this is specially local maximum. Here local minimum. Here increase in inflections. And here decrease in inflections. And these are critical points. Gradient of the tangent drawn to the curve at critical point is 0. That's the thing. Gradient of the tangent drawn to the curve at critical point is 0. That's the thing. Okay, write it. That is about critical points. So in graph also we need to analyze them. But in application of derivatives, we need to analyze local maximum or local minimum only. Okay. Right? Sketch and write this. This very simple mark, application of derivative, really simple type. So today we're gonna discuss past papers as well. Okay. Now same time use put this on as well. Take this. So here this type concave down, here this type concave up. Concave up, concave down. Here concavity we check by second derivative. Concavity. Can be obtained by f double dash x, second derivative. Here for concave up case, f double dash x positive. Concave down case, f double dash x negative. F double dash x negative. Okay, put that on as well. Concavity. Concavity. Here concave down, here concave up. Concave up we obtain by second derivative, concave down also we can obtain by second derivative. Then up case positive second derivative, down case negative second derivative. Okay, put them. Okay. Now we have increase in functions. Here there are three types. These are increase in functions. For all cases, f dash x greater than 0. F dash x greater than 0. Then as x increasing, y increasing. As x increasing, y increasing. Here this case, especially f double dash x positive, and for this case f double dash x negative, and here this case f double dash x 0. Then constant gradient, then when we differentiate gradient again we get 0. Then constant gradient at second derivative will be 0. Then here concave up, concavity, concave up gradient second derivative positive. Then here concave down second derivative negative. Then all three cases first derivative positive. These are we call increase in functions. Increase in functions. Then here as x increases, y also increases, no? Okay. Then similarly we have decrease in functions. We have decrease in functions. So here there are three cases again. Here three cases. Then for all case, f dash x negative for decrease in function. Then as x increasing, y decreasing, no? as x increasing, y decreasing, decreasing function. And for this case, especially f double dash x concave up, no, positive. And for this case, f double dash x 0. And for this case, f double dash x negative. Then we have two different function types, increasing functions, decreasing functions, increasing and decreasing. So in same single function, there can be increasing region and decreasing region, increasing region and decreasing region. Then increasing case, as x increases, y increase. Okay. Then for that case, positive gradient. For decreasing, negative gradient. Negative gradient. That means second derivative negative. Then here concave up, concave down. Concave up, positive second derivative. Concave down case, negative second derivative. Okay. Put them. Okay. Write them. Okay. Now, next part. See this one. See this one. You consider maximum and minimum. So take this point, corresponding x coordinate x equal a. Then here take this point x equal a plus delta. Delta means very small value. And take this point, that is x equal a minus delta. A minus delta. Okay. Then when you sketch a tangent here, we know that is parallel to x-axis. Here obtuse angle, and here acute angle. Therefore, when you consider dy by dx or f dash x at x equal a, that is 0, no? 0. Then dy by dx at x equals a minus delta positive, greater than 0. Then dy by dx x equal a plus delta negative, negative. Then similarly here, you consider x equals a, here x equals a plus delta, here x equals a minus delta. Here parallel to x-axis, here acute angle, here obtuse angle gradient. Therefore, dy by dx x equal a minus delta negative. Then dy by dx x equal a 0. Then dy by dx at x equals a plus delta positive, no? A plus delta positive. Delta means very small value. So anyway, at that point, gradient 0, then some point away, here right hand side positive and left hand side negative. Here right hand side negative, left hand side positive. Positive to negative variation, negative to positive variation. That's how we analyze maximum and minimum. So here sign variation of the derivative. Okay, put it sign variation of the derivative. Of dy by dx, dy by dx. This sun, because of this sun you can find critical point. Then derivative 0 point we call critical point. You better write here, better to highlight this sun. First derivative zero points are critical point. First derivative 0 points are critical point. Then here especially a value we call critical value. Here x equals to a, no? We say that is critical value. X equal a, that means derivative 0 position. X equals a position, critical value, then corresponding point, critical point. That's how we analyze. Do soon. Okay, then first derivative 0 position, critical point. Huh? Okay. So when you are doing application of derivatives, you have to identify critical point first. So that point belongs to maximum or minimum, no? Belongs to maximum or minimum. Then first of all, you have to identify critical point. Then critical point we obtain by checking derivative, no? Then derivative 0 position. Then first step you have to differentiate the function, then equate to 0, find values, that is critical values. That means x values, critical values. That value we can substitute the function, then we can get the point. Then we can get the point, that's the procedure. So again, before differentiating the function, we have to convert that into single variable like y equal fx. Okay, no multivariable functions we analyze, only single variable functions we analyze under A levels. Okay, write down. For applications of derivatives, follow the following procedure. First one, obtain the function which should be maximized or minimized. It should be maximized or minimized. And then convert into single variable function. Step 2. Differentiate the function. And find derivative 0 positions. Derivative position. Next step, check sign of the derivative. And identify minimum or maximum. Okay. Now I'll do this for simple function. You consider y equal x square minus 2x minus 3 function. So differentiate this dy by dx. Here 2x minus 2. Then check dy by dx 0 point. then 2x minus 2 0, x equal 1. Here we call critical value. Critical value. Okay. Then here critical value, get corresponding point, substitute 1. 1 square 2 times 1 minus 3, that is minus 4. Minus 4. Then here 1 minus 4 is the critical point. Therefore, by these two you say 1 comma minus 4 critical point. Critical point. Here this is single variable function. So now you check dy by dx sign. So you have to check with this critical value. X equals 1, less than 1 and greater than 1 case. X less than 1, x greater than 1, dy by dx sign. So here this is dy by dx now. So you take this one, greater than 1 value, here for greater than 1 value, dy by dx positive. And here less than 1 value, here dy by dx negative. Na? Then negative to positive variation we say minimum. Na? Negative to positive variation we say minimum. Here negative at 1 0, here positive acute. Then here local minimum. Therefore 1 minus 4 is a local minimum. Local minimum. That's how we identify. So by using quadratic type also we can analyze same. By using differentiation we can analyze critical points. Okay. Do that example. Okay, now let's start the questions. Take your past paper collection. Take past paper collection. Now I told you question number 14 pure paper part B will be application of derivative class. First identify the thing. Take 2024 part B B part. 2024 part B part. Just read it. Don't do. Just read. Just read. A cylinder with top and bottom is made to have volume 1024 pi cubic centimeters. Then volume given fixed volume. Let R be the radius of the cylinder, so that the total surface area S of the cylinder given by S equal 2 pi 1024 divided by R plus R squared. Then thereafter show that S is minimum when R equal 8. Then we have to analyze minimum. Then at the minimum we have to differentiate and equate to 0. That's the. Then when you are reading this question, you see what has to be minimum or what has to be maximum. So here we have to minimize S. Therefore S function S given in terms of R, then it is single variable function. No? S varies with R. Then you have to differentiate S with respect to R. You have to differentiate S with respect to R and equate to 0, find critical value and check the sign. That's it. Now just read 2023 part B part. Just read. Analyze the thing. It is required to build a fence of along diagonal of rectangular region of area K square meters. Then area given mean it is fixed. Then one side given X. You have to show that L squared equal X squared plus K squared over L X squared. So using general mathematics you can show. And hence show that L is minimum when X equals root K. We have to find minimum value of L. Then you have to differentiate L with respect to X. No? The function given single variable. No? Then you differentiate L with respect to X and equate to 0 and find critical value. And we have to show that that is minimum by checking the sign. No? By checking the sign you can show that it is minimum. Then go to 2022 part B. The shaded region given 45 square meters. That means area fixed. Then rectangular part has removed. Show that the perimeter of L. Perimeter given L equals 6x plus 54 over x. That is perimeter. Find the value of x such that L is minimum. Then you have differentiate L with respect to x. No? Differentiate L with respect to x and equate to 0 and you can go further. That's how we do. Then again last analysis. Go to 2021 part B part. Part B part, the shader region. Put there B. The shader region S of the adjoint figure shown a garden consisting of rectangular two sectors. So last line S is given, show that the perimeter P is of S given by 2x plus 72 of x. Then perimeter function given. We have to minimize perimeter. Then P single variable, you differentiate P with respect to x and equate to 0 and you can find corresponding x value. Very simple question. So very simple mark here. Definitely you get at least 6 and maximum 7. Okay. Then let's start from 2024 A-level question. Okay. Read and start sketching. (2024) Part B, B part. First to sketch. Cylinder, here cylinder. Top and bottom is made to have a volume of 1024 5 cubic centimeters. Let R be the radius of the cylinder. Let R be the cylinder radius. You take height simple h. Then volume you can write pi r squared h, 1024 pi. Simplify, h equal 1024 over r squared. Show that the total surface area. Then surface area, here two circular base, pi r square times 2 plus here outer surface area, here this part 2 pi RH, 2 pi RH, 2 pi RH, 2 pi r squared, 2 pi RH value, here you take from here, 1024 divided by r squared. Then cancel r. 2 pi r square, 2 pi 1024 over r. Then take 2 pi outside. Here 1024 divided by r and here r squared. So radius r positive. Radius r positive. Then here the function. Here this function, area function, surface area function, variation with respect to r, surface area. Here this is general mathematics, general mathematics, not calculus, just general mathematics. Then general geometry you apply and obtain the relation. Now thereafter, show that S is minimum when R equal 8. Then we have to find minimum S value. No? Therefore, you differentiate this one, differentiate S with respect to R, differentiate this. Then ds divided by dr, Here 2 pi constant, no? So 1024 divided by r. Here this derivative we say 1024 divided by r squared minus r squared derivative 2r. No? Then I told you to remind 1 over x derivative minus 1 over x squared. Then here 1 over r derivative minus 1 over r squared. Here we have constant. No? Directly apply them. So now here it is. Now you better to simplify this. Then ds divided by dr, simplify. Get common denominator. Take 2 outside. Then 4 pi. Here r cube. This goes to here r cube. 512 divided by r squared. Here 4 pi. R cube minus 8 cube over r squared. Now you take ds divided by dr 0. Then to get maximum or minimum value, you have to consider derivative 0 portion. Here we need to minimum s. Here for minimum s. For minimum s value, ds over dr 0. Then here 4 pi. R cube minus 8 cube over r square 0. Then r cube equal 8 cube. Then we get r equal 8. R equal 8. Very simple. You obtain the function, convert into single variable, differentiate, simplify and equate to 0, find the value. Okay, that's the procedure. Thereafter you check sign of the function. Sign of the function close to r equal 8. Sign of the function close to r equal 8. Then sign of ds over dr. ds over dr. About r equal 8. Here 8. 8 greater than 8, less than 8, but that is positive. Then you take this one. That is ds over dr. No? Then r less than 8, this part negative. R greater than 8, this part positive. Then negative to positive variation minimum. Therefore, at r equal 8, s is minimum. At r equal 8, s is minimum. That's how we do. Very simple part. You follow that procedure. Obtain the function, convert into single variable, differentiate, simplify, equate to 0 and check the sign. That's the procedure. Okay, again see the procedure. here you have to obtain a function. That means we have to minimize S now. We have to obtain function that belongs to S with single variable. So using general geometry and mathematics, you have to obtain that, convert into single variable. Then we have to minimize this one. Then to get minimum value, differentiate it. Then here simple differentiation step we have. No advanced differentiation, we just simpler differentiation type. Then differentiate, simplify and equate to 0. Then find corresponding critical value. No? Thereafter you check the sign. That's it. Okay. Then 2023 part B. 2023. Do alone. It is required to build a fence with along a diagonal of rectangular region of area K. Then K value you consider as a constant. K value constant area, okay? That one varies. So we have to minimize length L. Use general geometry. So if you have any doubt, do with me. Here x in meters, here L, capital L in meters, here rectangular shape, no? Take here y. Then area K square meters equal x times y. K square, no? Sorry, K. X times y. Then xy equal K. Then y squared equal by the Pythagorean theorem, or apply Pythagorean theorem, L squared equal x squared plus y squared. Then y mean K divided by x. Now you can take x square equal K square plus divide by x square. That's the function. L square equal L square equal x squared plus k square divided by x square. Show that L is minimum now. Now you have to differentiate that. No need to get square root. By taking similar relation, you can differentiate. Identify k is a constant. Okay, k is a constant. X is a variable. L varies with L. L varies with x. Then you have differentiate L with respect to k. Differentiate L with respect to k. No. Continue. Here this is general mathematics. These are general mathematics, not advanced mathematics. Differentiate L with respect to x. Then L square derivative, function of function 2L times dl divided by dx, x square derivative 2x plus k squared of x square derivative, k square times x to the power minus 2 derivative minus 2 x to the power minus 2 minus 1. Simplify to x minus k squared over x cubed, then x to the power 4 minus k squared over x cubed. Now take dl divided by dx 0 for minimum L. Therefore, x to the power 4 minus k square of x cubed 0, then solve this. X to the power 4 equal k square, you say x equals square root k. No need to put plus or minus. Here no need to put plus or minus because this is real application. Then real application x value always positive. Don't put plus or minus root k. Okay, we can directly write x equals root k only because real application x is positive. X means length, no? Then length always positive. That's why we can take positive value directly. Okay, that is critical value. Then check dl divided by dx sine. Then here take critical value root k. Then about this point you have to check. About this point you have to check. Then if you consider here less than root k, here negative, greater than root k, this part greater than positive, then minimum. Therefore, when x equal root k, L is minimum. When x equals root k, L is minimum. L is minimum. That's how we do. '23, that is. Thereafter you can move to 2022. When you take dl divided by dx 0, this term, full term will disappear. Then don't worry about this L term. Don't worry about that. L times 0. Okay. Then you go to 2022 question and start. Okay, here we check dl divided by dx sign. Okay, dl divided by dx sign. We have to show that that is minimum. So here critical value. So you need to consider critical value. Here cross set you consider. Here k greater than root k, x value greater than root k, x value less than root k. Okay. Here x equals k, we know x equals k, it is 0. X equal root k, it is 0. Then you're going to check dl divided by dx sign. dl divided by dx mean here this one. L times dl divided by dx. Here L mean length, no, positive. Positive. L mean length, positive. Then we don't worry about that one. Then when x value greater than root k, x value greater than root k, here this part greater than k square. No? Here positive part, positive. When x value less than root k, here this is small. No? This part small than k square. Therefore it is negative. Then negative to positive variation minimum. Negative to positive variation minimum. That's how we analyze. Start 2022. Do alone. Here all variables are given. Variables are given and the relation already given. Relation already given. Then that means path given. Then you have to go along that path. That's it. 2022. Part B. Here the figure. If you have in doubt, do with me. Others do alone. Y, x, 2y. Then here area fixed. 45 square meters. Then 45 equal, here 2y times x. 2y times x. That means times 2 plus x times y. Then 45 5xy. Here y equal 9 divided by x. Take this relation. Now the perimeter L. Here 2y, 4y, 5y, 6y. Here 3x, 4x, 5x, 6x. Here the perimeter. Now you can convert into single variable. No? Then you convert that into single variable. Now by this you can replace y. 9 of x, 6x. Now 6x, 54 of x. Here it is. Then x, y both are positive values. Here the function. Now L perimeter we have to minimize it. Now that is in single variable. Then you differentiate that. Differentiate the function now. Then check dl divided by dx. 6x derivative 6. 54 over x equal 54 over x squared. Then take 6 outside, x squared minus 9 over x squared. Then you have to solve dl divided by dx to 0 to get minimum. Therefore, dl over dx 0. Here 6 x squared minus 9 over x squared 0, then x squared equal 9, x equal 3. Here no need to write plus or minus 3 because x positive. Since x positive, x means length, no? Then since x positive, don't worry about getting negative values. Okay, but just pure mathematics we get plus or minus 3. In pure mathematics we get plus or minus 3. In algebra we have to take that. But here application, side length positive, then you can consider only positive values. Then x equals 3. Now you check dl divided by dx sine. About this x equals 3. Here 3, 3. Less than 3, greater than 3. Then here you have to stop at 0. Then greater than 3, here this part positive. Less than 3, here less than 9, no, negative. Then negative to positive variation minimum. Therefore, at x equal 3, L is minimum. L is minimum. Find the values of x such that L is minimum. That's it. So while doing that, so we have to know some geometrical things. So I'll just revise it. Take this. Here when you consider arc, here arc, and here a sector, take this angle alpha radius r, then here arc length is equal arc theta. Arc theta means 2 alpha. I'll take here theta, arc theta. Then here area, half r square theta. You need to remember these geometrical relations, okay? Here, when you consider a sphere, or here take circle, Then here radius r, we know that one. Pi r square no area. Pi r square. Here a sector. You know square and rectangle. Here xy. Here area xy. These are general things. No? Now you consider here a sphere. A sphere, radius r. Then volume 4/3 pi r cube. And area 4 pi r squared. You have to remember this. Huh? For sphere, surface area 4 pi r squared. Then volume 4/3 pi r cube. 4/3 pi r cube. Now here a cylinder, radius r, height simple h. Here volume pi r squared h, area here 2 pi r h. Here 2 pi r h and pi r square twice. And here a cone, height h, slant height L, radius r. Then volume 1/3 pi r squared h, surface area here curve part pi r L plus pi r squared. Here pi r squared, full surface area. Here pi r L, pi r squared. That is a cone. Okay. These geometrical things you have to remember. You have to remember that. Huh? Okay, go to 2021. Go to 2021 A-level question. Continue. Continue. 2021 question. Part B, B part only. So here the figure. Y, X all are given, angle 3 pi of 8. The area 36 square meters. Then 36 equal, here rectangle XY, here sectors, 2 sectors, 2 times half, R mean X, no? X square, theta mean 3 pi of 8. 3 pi of 8. Then 36 XY, here 3 pi divided by 8 X. Then Y, take Y, 36 minus 3 pi divided by 8 X, no? Now divide by X. Here it is. Here X squared 3 pi over 8X. This is Y. Then perimeter P. Perimeter, here Y plus Y, 2Y, X plus X, 2X, here R theta, here R theta, R mean X, theta mean 3 pi divided by 8 times 2. Two y plus 2x, 3 pi divided by 4x. Now put this y here. Y equal 36 of x, 3 pi x divided by 8 plus 2x, 3 pi divided by 4x. Now here 3 pi divided by 4x you can cancel. Then here 2x, 72 of x, that is perimeter. Then here x greater than 0, that is general geometry. First write area relation, then write perimeter relation and manage it to get the result. Now here we have to minimize P. We have to minimize P when let's find that. P, then differentiate dP over dx, 2 minus 72 over x squared. Here when x equals 6, when x equals 6. Now simplify. Take 2 outside, x squared minus 36 divide by x squared. Now dP over dx equals 0. To get minimum value, minimum P. Then simplify. 2x squared minus 36 of x squared 0. Then x squared 36, x equal plus 6, x positive value, no? Then x value 6 only. Now you have to show that that is minimum. Then dP divided by dx sine. Do alone. Here 6 less than x, greater than x. Here we have to check sine of dp over dx. Here you have to take this. Then less than 6 value negative, greater than 6 value positive. Here positive, negative. Here you better to stop at 0 because x positive no. Then negative to positive variation minimum. Therefore at x equals 6, p is minimum. At x equals 6, p is minimum. Here we follow one simple technique. First get in function, then differentiation, and solve dy by dx 0 and check the sign. That's it. Very simple procedure. Okay, then 2020. Part BB. Here dustpan shown in the figure and all the values are given. It's given that its volume given. Here the figure. So here volume given 4500 cubic centimeters, that is x squared h, 4500. Then h equal 4500 divided by x squared. Then surface area given S equal 2x squared plus 3xh. Surface area given, na? No need to find. Both are given. No need to find. Show that S is minimum when x equals 15. Now you have to differentiate this. Before that you convert this into single variable. 2x square 3x h mean 4500 divided by x squared. Then single variable function 2x square 3 times 4500 divided by x. Here single variable function. Now differentiate x by x. Here 2x square derivative 4x. 3 times 4500 divided by x squared. Here 1 over x derivative minus 1 over x squared. Then simplify little. X square 3 times 4500 x squared. Now you take 4 outside. Here x cubed. Now 4500 divided by 4. Here 125 times 3. 125 times 3. 3375. So here values are all, answers are given, no? Answers are given. Okay, here answers are given. Then you follow procedure, ds divided by dx equals 0. Therefore, x cube 33750, then x equals 15. x value 15. මෙතනද අමාරුවෙන් මේ x cube ගේ value හොයන්න එපා. 15 දීලා තියෙනවා. ආය අමාරුවෙන් ඒක හරිද කියලා හොයන්න යන්න එපා. ඒක අරගෙන check කරලා බලන්න එච්චරයි. x equals 15. Then ds over dx sign. You check this sign. Here about this 15 value you have to check. Less than x, greater than x, 15. Then less than 15 here negative. Greater than 15 positive. Then negative to positive minimum. Negative to positive minimum. Therefore, when x equals 15, s is minimum. S is minimum. Complete. Okay, then you analyze that all questions are similar types. Okay, first we have to build the function, then we have to convert that into single variable, then we have to differentiate and equate to 0, then find critical value. Okay, then finally you have to check sign of the derivative. Okay, okay, let's have a small interval.